It's certainly been a while, but we happen to be back. Today we will be going over a calc AB, um, what I like to just call graph analysis. I don't know. That's the best I can come up with. This question really tests your knowledge about the fundamental theory of calculus and the relation between integrals, derivatives, and just your function. Um, having taken Calc BC, I feel like you do the same thing. So say A, B, but it's really similar. But regardless, we'll get started. So as you see, we have the AP question here. I will be showing my work, elsewhere. But first, what you should really always do when you have a question is mark it up, get the key information. So before I mark everything up, I'm just going to run through the questions real quick, the parts. So we need to find all x coordinates where f has a relative maximum and give a reason, whatever that's implied. So we are finding, that's actually not that important. We are finding where f has a relative maximum. So that is part one. Now on what open intervals contained in -3 to 4, that's just your entire bounds right here, shown in the graph, is the graph of f, both concave down and decreasing. Give a reason for your answer. This is one of the classic interval questions, open intervals indicating, you can't be concave down or decreasing instantaneously, especially at the bound. Now find the x-coordinates of all the points of inflection for the graph f, give a reason for answer. And then given that f of 1 equals 3, write an expression for f of x that involves an integral. So kind of tells you there you're going to need integral. We're given f prime. We need some, we'll get to that. We'll get to that. Now let's look at the description. So we have a graph of f prime that is extremely important to take note of. The derivative of a twice differentiable function. And this is really just like a go ahead. That's telling you f prime of x exists and f double prime of x exists. That is very necessary because we're going to need it for our later questions. On the interval -3 to 4, inclusive, that's just what we see in our graph. The graph of f prime has horizontal tangents at -1, 1, and 3. So let's take a peek at that real quick. Let's zoom in. We have -1. So we're really saying there's a straight line here. It's not going to be perfect. But we have a straight line here, straight line here, straight line here. And as we know, the definition of a derivative is the slope of the tangent line. Or that's how you find the derivative. So when we see the slope of the tangent line to this point, we have to ask ourselves, what is the slope of these lines? Because they're directly horizontal, the slope, or m, is equal to 0. So this is actually this is really just telling you that the second derivative at these points are equal to 0. Because remember, we already are using our first derivative. Trying to just tie that idea up, but essentially we will be needing this information that the second derivative is 0 at these points, for I think just B and C, or mainly C. Now the areas of the region are bounded by the x-axis. Okay, that's great. and the graph of f prime on the intervals negative, okay, and the graph of f prime on the intervals -2 to 1 and 1 to 4, 9, 12 respectively. Okay, so we really don't have any bounds here. That's fine. It tells you the rest. So -2 to 1 would be this area. And we know that this was 9, or is 9. Now for 1 to 4, likewise this area, and this is 12. And I mean, that's kind of the setup we need. Now we can kind of proceed. Yeah, so just as a recap, I'm taking this pretty slow. We have the graph of f prime. Eventually, we're going to find an equation for f of x, but we see already that we're using the second derivative, and we see already that we have the integral. So already we're using all parts of the equation. If it doesn't make sense yet, that's okay. We'll explain in more detail on each of the parts. So for part A, our goal is to find all x-coordinates at which f has a relative maximum. So the first step when finding a relative maximum, just local extrema in general, is we want to find our critical points, or critical values. So our critical points is what I'll call them. This is when your first derivative, just do it here. This is when f prime of x is equal to 0. Now, our whole equation, God, this is annoying. Our whole equation, or this graph, is of f prime. So we're really looking for, when it's crossing the x-intercept. So, it's y0 here, y0 here, and y is 0 here. Now, for the critical points, we are also going to include -3. Yeah, we'll include -3, but that won't. I don't think we have enough information there to determine that it's a relative maximum, because we don't know where it is before. We don't know if it's positive or negative positive. So for now, we'll just table that -3. But we will use our -2, 1, and 4. So critical points are -2, 1, and 4. So for all of these, f prime of -2, 1, 4, it's equal to 0. Now we need to test what type of extrema it is. So in the case of a local maximum, we can draw this out real quick. So if we have a graph of f of x, it's like scribbling, whatever, this would be, a local maximum, also this. But we need to analyze the derivative. So we're increasing, then we're decreasing. So if I'll just do a plus and minus. If we were to graph the derivative, you would see something positive that's actually kind of decreasing, and it's going into the negative axis. That's a very, very rough sketch. And we see we're in the positive quadrant, or positive axis, the y value is positive, and then we go into the negative value. So this would be plus to negative. F prime I'm trying to say this succinctly. F prime goes from positive to negative for a max. And then on the contrary, I won't write it for this purpose, but f prime for a local minimum would go from negative to positive. And this is just, you can, you just look at it kind of graphically. We're decreasing here, increasing here. And this is a local minimum. So for -2, let's look at -2. For -2, we are increasing, or, okay, first, we have the graph of the derivative. So if we recall down here, we kind of have it in the positive two quadrants and then goes into the -2 quadrants. So around -2, we start positive, go negative. So that actually is already a local extrema, which is a local maximum. Now at 1, we go from negative to negative. So that's not any local minimum or maximum. That's going to be something else. And then at 4, this is because it's a bound, it's also not enough information. So like we don't really know what's going on after this. So we cannot say. That's also why we don't really, I guess we won't use -3 as a critical point here. In other cases, we probably would. So, we kind of overdid this problem already, but we can say that the f of x has a local maximum at x equals -2. Let's say because f prime of -2 is equal to 0, and and I will say f, just get the method they want. This increasing to decreasing thing works. You can also just do a concavity check. So it should be fine if you do, if you just say f prime goes from increasing to decreasing, indicating a local maximum. You probably, so I know that, that is the right answer. Let's just go to the AP docs real quick and look. So they're okay with, there's, first obviously do their f prime equals 0 preliminary checks. Yeah, -2, 1, and 4. That's what I said. And then f prime changes from positive to negative and -2. Okay, so that's what they did as well. So I guess that's good. I don't think you need to use these many words. Like if it's on the AP exam, I wouldn't really test it. I would say everything that I can think of, but whatever. I do not want to be taking this much time. I have to talk too much sometimes. So B, on what open intervals contained in these bounds, to shown in the graph, is f, not f prime, both concave down and decreasing. So okay, so concavity relates to the second integral, decreasing relates to the first derivative, second derivative and first derivative. Apologies. So first, I like to start off easy and say are the intervals where we're decreasing. So for the intervals that are decreasing, f prime is just going to be negative. So that's literally just going to be -2 to 1, or yeah, we can union it. So we'll say -2 to 1, and then end 1 to 4. So I will just quickly write this down here. So decreasing, I think it was -2 to 1, and we'll union, because 1 is 0, so it's not increasing or decreasing. 1 to 4. I believe that's correct. -2 to 1, 1 to 4. Perfect. So that's decreasing. Now let's check concave down. So when we're checking for concavity, concave down, when we're checking for concavity, we're going to take the second derivative and say, is it positive or negative, essentially. So concave up would be positive, and concave down would be negative. So since, again, this is the graph of our first derivative, we can kind of just say in these sections, like -2 to -1, we see we have a negative slope this entire on that entire bound, or more accurately, a negative derivative. So it's decreasing here. So f, the second derivative of f is negative. I'll write that down. And essentially, you can just look at that entire graph. So like -1 to 1, that would be positive. So that would actually be concave up. And then negative again. So we're looking at another concave down and then up. So where are these decreasing? Well, we can actually say from -3 to -1, because again, this that section is just decreasing. We have our graph of f prime here, and also from 1 to 3. So it's -3 to 1. Okay, already forget it. -3 to -1. Oops, and 1 to 3. -3 to -1. 1 to 3. Union 1 to 3. And now we just, I'm just going to abbreviate it, concave down. We just find the overlap. So this is -2 to 1. This is -3 to -1. So we can start with -2. And then we go to -1. That's the only part that's inclusive there. Now we have this 1 to 4, which 1 to 3 fits perfectly in that. So I'm going to get that. Hopefully that makes sense, because I really did not explain that well, but it's essentially, you could like box the graph parts and just see where it overlaps. We're just looking for overlap here. Anyways, if that doesn't make sense for you, I would just refer back to the graph, like say, oh, box this is decreasing, box this, and then maybe in a different color, a different shape. So like, oh, this is concave up, this is concave down, just shade in the overlap. That is, this graph might probably like very wrong, so don't use that as an example. Now for C, find the x-coordinates of all points of inflection of the graph of f. So this is when we're actually going to go back to what is said here, where it says f prime is horizontal tangents. Horizontal tangent, it's a tangent line. The derivative is the slope of the tangent line. It's essentially saying the second derivative at these points is equal to 0. And that is our precondition for a point of inflection. So, yeah, I mean, I think all we have to do for this is say, I guess we have points of inflection at x equals -1, x equals 1, and 3, since f double prime, at these points, I'm just doing like a little shorthand, is equal to 0. And that is not the only check, because is our thing. That is not our only check, because there is something I'm missing, and yes, that is. So if we had, say, man, I think I'm just confusing myself. Another condition for the point of inflection is that you're going from increasing to decreasing or decreasing to increasing. So if we just quickly visually analyze these, we're going decreasing, increasing, then increasing, decreasing, and then decreasing, increasing. So all those meet it. So I'm just going to do like some really shorthand thing. You might want to individually say like, oh, this one's going from increasing to decreasing, or this set, I think it's these two, maybe. These points go, it would, in this case, it would be the second derivative again, I guess. F prime goes from plus 2 minus or minus 2 plus at these points. Just want to double check that that is in fact the second derivative. Yeah, because we have the graph of the derivative. Once again, I'll say that like 12 times in this video, and decreasing. So that would be the second derivative. All right. Finally, like the somewhat fun problem part. I don't know. I find it a little fun. Given that f of 1 is equal to 3, write an expression for f of x that involves an integral. So this is going to be relating to the fundamental theorem of calculus that states, I want to make sure I do this right. I think this would be part 2, not completely solid. It also does not really matter right now, but let's say that the integral from the bounds a to b of f of, let me say, f prime of x, yeah, no, this is right, of f prime of x dx is equal to f of b minus f of a. Yeah, I think that's right. So now, again, I think this is the second part of the theorem. But regardless, we'll just extrapolate this for all of our purposes. Okay, right. So we know that f of 1 is equal to 3, and that's our only known. So our hands are a little bit tied. We have to say that we have to start from 1 and go to x. Then we can call this equation g of x. I don't think it told us a name. So we will say this, slap f prime into that, dx, is it of x? It's of x. Actually erase this for now, and just using this theorem of calculus, we will say that f of x is, and this is equal to f of x minus f of 1. Sorry for being a little slow. Now we just add this to this side, and we will get that f of x, write that a little better, f of x, that was not better, f of x is equal to f of 1 plus the integral of from 1 to x of f prime of x dx. And this is 3 right here. Okay, so that is our general equation. Now it says we need to solve for f of 4 and f of negative 2. So we'll just plug it in. F of 4 will be equal to 3 plus the integral from 1 to 4 of f prime of x dx. Now the integral from 1 to 4, x, 1 to 4 is 12. That's just stated in the problem. But that is a little incorrect because remember, this is the area. Areas are always going to be positive. However, the integral from 1 to 4 is actually negative. It's just on, the y values are negative. So we would actually have to say 3 plus negative 12 to get negative 9. Similarly, f of negative 2, like we could say that's 3 plus the integral from 1 to negative 2. Okay, do not mean to press that. 1 to negative 2, f prime of x dx. So 3 plus, we'll scroll up. It says from negative 2 to 1, it's 9. But remember, our bounds are actually 1 to negative 2. We're going backwards. You could also say, because backwards doesn't really make too much sense, but we could say the negative integral from negative 2 to 1 of f prime of x dx. That's just one of your basic rules. So in this case, Remember, the area itself is 9, but this integral, because we're going backwards, instead of doing -9, we're just going to do our +9 and get 12. Hopefully that made sense. If not, just know that you can reverse the bounds, slap a negative sign in front of it, and then you're doing the same integral. But yeah, I mean, that is actually the end of this. Let's finish this. Like f of 4 equals -9, f of -2 equals 12. All right, so, that was a lot of talking, but I kind of, just wanted to include all the explanation. Hopefully this is of some help. I will hopefully be doing more in the future. It's my setup. I had to like pull out my dusty laptop because I couldn't get to work my new one. So hopefully I'll fix that and be more inclined to record. But anyways, thanks for bearing with me, and hopefully this helped. Until next time.